Okay, so starting this unit, we are talking, so Unit 7, Day 1, identifying linear functions. For the next bit, we're going to be talking about linear functions. Okay, so for quite some time, we're going to talk about these. So we need to take this pretty straightforward. All right, so first thing we're going to talk about is the vertical line test. Okay, we actually used this in the last unit to tell if things are functions or not. And so what it said is that if you can draw a vertical line, okay, and it only hits this graph once, then it's a function. If it hits more than once, it's a problem. Okay, so I usually take my pencil or something and I kind of imagine it going over, and as I look, it's touching my graph once there, once there, once there, once there. It never actually hits it more than once. And so since it only touches once, we can say that this relation passes the vertical line test, and so this is a function. Okay, so the first thing we're asking is it a function? So identify if the graph is a function. If it is, decide if it's a linear function. Okay, so first, number one, is that a function? If I take my vertical line, only hits once, which means my x's don't repeat. So that is a function. Now, since it's a function, is it a linear function? And this is saying, okay, is it a line? And yes, as a matter of fact, it is. Okay. Okay. Next, is this a function? So if you take your vertical line, I always hit once. Okay, I can't ever hit it twice. So this one is a function. And now the question is, since it is it a linear function? No, because it's not a straight line. It's kind of U shape. All right, number three, is it a function? So could I put a vertical line and never cross this thing twice? Matter of fact, I can. There's one place I could put it, and it's right on top of it. Okay, in that case, so it's like this x right here has lots of different y values that match up with it. So this one is not a function. And so, yeah, so it can't be a linear function, okay, because it's not a function at all. So we're just going to leave that one blank. All right, so we only go on to the second question if it is, in fact, a function to begin with. All right, number four. Is this one a function? So to know that, we need to say, can we put a vertical line somewhere and cross it twice? As a matter of fact, I can. In fact, I can draw one right here that hits that thing twice. So that is not a function. And so we're not worried about if it's a linear function or not. 5, take my line. It's only going to cross once the whole time I'm there. So it is a function. Is it a linear function? Yes, okay, because it is a line. Okay, now here, the important thing to note is the difference between this one and this one is vertical line test. We have to hold our pencil straight up and down. So in that case, that one does not work. That one does. Number 6, is it a function? It passes the vertical line test, so yes. Is it a linear function? No. I mean, it's made up of two lines, and there's a line here and a line here, but altogether, no, it's not a linear function. All right, so number 7, which of the following is not a function? Okay, so this is where our vertical line test comes in handy. So for f, is it ever going to cross twice? No, it's not. Okay, so that one is a function. I'm going to actually look at all these first. This one, is it a function? So actually right there, if I could cross that one twice. So that one is not a function. G, is that ever going to cross more than once? No, that one is a function. This was same thing. Okay, now at first glance it actually looks like it crosses right here, but that part of the line is not there. It's open, so it's only at one, that x only has one y. It's that one that's filled in. And same thing here. That x only has one y, the one that's filled in. So that one is a function. And so since they asked which one is not a function, H is our answer. All right, same sort of game with number 8. Which one is not a function? So let's see. It looks like we have a vertical line test issue right there. so that one's not a function. This one, those no x's repeat, so that's a function. Same thing we had over here, Okay, there's that x has one y, that's where it's filled in. So that one is, and that one is too, so that means C is our part that's not a function. Alright, so carrying on. Is this a linear function? Okay, now here's how we're going to tell this. Linear functions have a common first difference in y values when the difference in x values is constant. Okay, so if I were looking at this right here, when the x value is constant, these are all changing by 1s, plus 1, plus 1, plus 1. Then the y values are going, first it goes down by 5, down by 3, down by 1. So are these a common first difference? No. These numbers all need to be the same. So that one is not a linear function. This one right here, as they're going up by 1s, these are going up by 2, by 2, up by 2, so yes, that one is. And this third one, as the x's are going up by 3s, the y's are changing in these different amounts, 3, 1, and 2, so that one is not. So we're looking for the first differences in the y values to be the same when the difference in the x values is constant. So, number 9, we're going to look at the differences in the x values. So first, as we go from x to x, so that one's going up by 1, up by 1 there, up by 1 there, 1 there. Okay, so this is a good sign. So the x's are constant. The change in the x's is constant. So now we want to inspect the y's. So that's going down by 3, down by 3 again, by 3, and down by 3 again. All right, so I guess we should have approached this first. Is it a function? So do the x's repeat? No, they do not. This is a function. And now, since our first differences are all the same, this one is also a linear function. Okay, number 10, is it a function? So we don't want our x's to repeat in this case. So do our x's repeat? Yeah, right here. Right here. In fact, all these. All the x's repeat. So that one is not a function, so it cannot be. Oh, actually, we need to leave this in blank. We can't tell whether it's a linear function because it's not a function. Okay, number 11. First thing we'll do is we'll look at the change in the x's. So these are going down by 1. So minus 1, minus 1, minus 1. The y's, well, how much is that changing by? From 7 to 7. Well, I could add 0, that wouldn't change anything. So 0, 0. So when the x's, the changes are all constant, the y's are actually all constant as well. All right, so do any x's repeat? This one. No, they don't. So this one is a function. And since it is, and the first differences are the same, that is a linear function. All right, number 12. First, I'm going to look at the change in the y's, or the x's. So up by 2, up by 4, up by 6. I think I can stop there, but I'm going to look at these anyways. Plus 12, plus 18. Okay, now the key thing we set up here, when the difference in the x values is constant. Okay, so something that I notice here is that the x values are not constant. But what I can do, and I may have to do this occasionally, is if I look at how much the y is changing compared to the x. So the y compared to the x is 3. This one right here, the y compared to the x, the 12 divided by 4, is also 3. And 18 divided by 6 is also 3. So this one actually is going to be a linear function. Okay, so first the x's don't repeat, so it's a function. And it is a linear function because the change in y compared to the change in x actually comes out to be the same for those. Okay, so 13 would be a little more traditional compared to the other ones we did, so let's look at the change in the x's first. looks like they're all changing by 1s. The change in y, plus 3, plus 5, plus 7. Okay, the x's do not repeat, so it is a function. Okay, but when the change in the x's are the same, the change in the y's are not. So this is not a linear function. Okay, so starting with 14, I need to think about this. So we've been talking about tables this whole time. Well, here we don't have a table. Okay, so first thing I'm going to do is actually create a table. So x and y. All right, so x will have 2 matches up with 4, 5 matches up with 3, 8 matches up with 2, and 11 matches up with 1. All right, so I want to see the change in x and the change in y. So let's see, it's going up by 3, up by 3 again, up by 3 again. Okay, so that's a good sign. We want the x's to change the same amount. Now let's compare that to the change in y. Let's see, minus 1, minus 1, minus 1. So when the x's have a constant change, okay, then the first difference is common here. They have the same change going on there. So this one is in fact going to be a linear function. And I got ahead of myself. This one is a function because the x's do not repeat. Okay, let's do the same thing for number 15. First thing I'm going to do is make a table. So negative 10 matches up with 10. Negative 5 matches up with 4. 0 matches up with 2. 5 matches up with 0. All right, so the x's do not repeat. We have all 4 different x's. So this one is a function. Now we need to look at the change here to tell if it's linear. So this is going up by 5. Up by 5, up by 5, and then over here we have minus 6, minus 2, minus 2. Alright, so the x's differences are the same. So are the y, the first differences in the y, the same? No, they're not. So this one is not a linear function. All right, so for the next few of these we're going to do the same thing. First thing we want to do with number 15, or number 16, is make a table. So again, determine if the mapping represents a function. If so, is a linear function. So same sort of thing, except we're going to take 3, 5, 7, and 9. Okay, and the numbers they match up with here. So 3 matches up with 5. 5, the arrow goes to 4. 7, the arrow goes to 3. And 9 matches up with 2. So first, do the x's repeat? Or said another way like this, these arrows, each one of these should have 1 arrow, every x is 1 y. So is this a function? Yes, it is. Okay, so just manage about the changes now. So the change in x is plus 2, plus 2, plus 2. And the change in y is minus 1, minus 1, minus 1. So when the changes are constant in the x's, the first differences in the y are all the same. They're constant. So this one is a linear function. All right, next, number 17. I'm actually not going to have to make a table for this one because, first question, is it a function? It's not. So what tells us that it's not a function? Well, you can look at it 2 different ways. If you look at the up here, it looks like the x repeats. And if you look down here, this guy is shooting 2 arrows. As I said a while back, that is a problem. Everybody should shoot one arrow. Every x has 1 y. So this one is not a function. So there's no way that it can be a linear function. Okay. Number 18. Which of the following is not a function? Okay, not a function. So in this case, to be a function means that x does not repeat or Every x has 1y. So for it not to be a function means that x does repeat, or every x doesn't have 1y, or has more than 1. Okay, so see here. So 1, 2, 3, 4. Okay, the x's don't repeat, so that's a function. So in that case, we want not a function, so that one's not it. Do the x's repeat on G? No, they don't, so it is a function. We don't want the function. 1 repeats. It actually goes to has 2. So this x has 2 y values. So that one is not a function, which is going to mean that's the one we want. But if I look over here, 1, 2, 3, 4. Okay, x's don't repeat. It is a function, so it is h. All right, number 19. Which of the following sets of points could not represent a function? Again, that means that x. So a function means that x does not repeat, or every x has 1y. So we're looking for the opposite of that. So we look in the x's. X does not repeat. Every x has 1y. So we're looking at the x's. So 5, 6, 7, 8. Not an issue. Okay, that one is a function, so it's not it. -3, -2, -1, 1. The x's don't repeat, so that one is a function. We don't want it. 0, 1, 2, 3. Those x's do not repeat. It is a function, so that's not the one we want. -1, 8, -2, -2. Well, this one shows up twice and it actually goes to 2 different y values. So that one is not a function. So that's the one we want. Alright, so far we have talked about determining if we have linear functions with tables, with graphs, with mapping diagrams, and the last type of thing we're going to look at are equations. Okay, so a linear equation is any equation that can be written, that's an important note, that can be written in standard form. Okay, now to tell that we really need to know what standard form is, and so here we have it. Standard form of a linear equation is ax plus by equals c, where a, b, and c are all real numbers, and a and b are not both 0. So it'll be of the form a times x, or a number times x, plus another number times y, equals some other number. Okay, so we want to be able to write it that way. It may not always look just like that, but we should be able to write it that way, to get it that way. Okay, so some things to notice about the standard form is that when something is in standard form, x and y both have exponents of 1. So what that means is we don't have an x squared or an x cubed or anything like that. Also, x and y are not multiplied together. They are their own separate terms. X and y are not denominators. They are not exponents. They are not radical signs. So I have some examples to show you for that. Okay. So some examples of linear functions and then not linear functions. So here are my examples. Okay, so over here, I'm just going to look at my examples for now. 2x plus 3y equals 7. Okay, that looks kind of like this, where a is 2, 3 is b, and c is actually 7. Okay, you have something different that looks like here. Y equals -3x plus 1/2. Okay, it isn't written like this, but it could be. I could actually add 3x to this side and get 3x plus y equals 1/2. Okay, I could make it look like that. X equals 7. Okay, I'll show you in a second how that really is linear. And then this right here, y equals 8. I'll show you also how I can do that. Okay, so the non-examples though, okay, easier to spot because they look nothing like that standard form. X squared minus y equals 0. The issue there is that x has an exponent of a 2. Okay, it has an x squared. The standard form does not have an exponent on the x or the y. They're exponents of 1 automatically. Okay, so x squared, not it. Alright, x times y equals 4. Okay, so again, x and y are not multiplied together. They have to be their own terms. They have to be added in some way there. All right, y equals 2 to the x power. Again, looks nothing like that. Okay, we have an x as an exponent. Here we have an x in the denominator of our fraction. Okay, x and y are not denominators. That can't happen. And then let's see, we have radical signs, so that we shouldn't have anything like this, a square root of something. So those are some good examples to hold on to. Okay. So we're going to look at those as we go through these. Okay, number 20. 3x equals 2y plus 4. Now at first glance this does not look like it's linear. Let's go back up here, ax plus by equals c. But I can make it look like that. Okay, so what I'm going to do is I'm going to subtract 2y from both sides. Okay, if I do it to one side, I can do it to the other. Okay, so this is perfectly legal. So I get 3x minus 2y equals 4, because that's a zero pair there. Now, does that look like that? Ax plus by equals c. It looks almost exactly like, in fact, a is 3, b is negative 2, and c is 4. So this one is a linear function. Linear function. All right, so our choices here are that they are linear functions or nonlinear functions. So in that case, I can make it look like that, and that's the goal. I want to be able to make it look like that standard form up there. Okay, 21. X equals negative 8. Okay, at first glance, again, this one does not look like standard form. Okay, we've got a x plus by. There's no y in this one. Okay, but I'm going to pull a little trick here. X plus 0y equals negative 8. Okay, now hopefully you can agree that I have a number times x plus a number times y. Okay, 0, that is a number, equals negative 8. Does that look like standard form? Matter of fact, it does. A is 1, b is 0, and c is negative 8. So this one is also linear function. Okay, 22. Now this one is just perfect because I picked my non-example up here really well. X times y equals 4. X and y cannot be multiplied. Okay, so no matter what I do, I could try dividing by things, I could try subtracting things, but no matter what I do, this one is never going to look like standard form. So this one is non-linear. Okay, 23. X squared plus equals 2y plus 4. There's a big problem staring me in the face, and that is this thing right here. X and y should have exponents of 1. That is an issue. No matter what I do, there's no way I'm going to be able to get rid of that x squared right there. That's squared. So this one is nonlinear. Now, usually the nonlinear ones just kind of stare at you. You can tell there's something wrong with them. 24. Something is glaring at me there. This radical. Okay, I want it to look like this: ax plus by equals c. So this nonlinear. Okay. All right, 25. I don't see anything wrong with that, and so that's a good sign. That means I might need to see if I can adjust it. I don't see anything wrong. Nothing is just glaring at me that there's a problem, like a square root or a squared or x and y being multiplied or things like that. So I'm going to pull the same trick I pulled over here. 0x plus 1y equals 12. Do you agree these two are the exact same equation? Okay, because you ought to be able to convince yourself of that really 0 times anything is like it's not there. 1 times anything is the same as just having a y. So you should be able to convince yourself that does look, that these are two the exact same equation, and this now looks kind of like our standard form we've got. So this one is a linear function. 26, we have 4 divided by x equals y. Okay, now I'll be honest. Immediately I think, oh, well, maybe I could rearrange that. And I'm going to try that real quick, but I'm going to show you that why this isn't going to end up working. Okay, but at first glance, I think maybe I can fix this. Well, that means I need to multiply by, I want to get an x out of the denominator, so I'll do x over 1. And so I get 4, let's cancel out, equals x times y. Okay, now I see a real problem. Okay, we have x and y multiplied. That is not good at all. Okay, so this is non-linear. So if it looks like you might be able to fix it, then there's a potential there, so try it. But in the end, don't be afraid to just say, okay, this one doesn't work. I can't fix this one. 27. Okay, so the problems that we said we're looking for are x and y having exponents of 1, x and y having exponents of 1, x and y not being multiplied together, x and y not being the denominator, exponents are radical signs. So if I go back over here, okay, x and y both have exponents of 1, right? There are no squares or things like that. Let's see, x and y aren't multiplied together, at least not the way they are. X and y are not in the denominator. That's in the numerator, so that's okay. Let's see, we don't have any exponents here. Or x is not an exponent, y is not an exponent. There are no radical signs, so I can't find anything wrong with this. So that's why I'm going to try and see if I can adjust it. So let's see, I want x and y on the same side. That's one thing. Now I'm going to see if I can rewrite this. This right here is the same thing as saying 1/3 times x. Right, because there's always a understood 1 there. So that's the same thing as 1/3 x equals 15y. Okay, so all I need now is I need x and y on the same side. So I'm going to try this. Subtract 15y. So that means I have over here 1/3 x minus 15y equals 0. So my question for you is that in standard form? If so, what's A? The number in front of the x is 1/3. What's B? The number in front of y. So that's negative 15. And C? 0. Do you agree that does look like standard form? I believe so. So this is going to be linear. And 28. Any issues you see right away? So x and y having exponents of 1. Okay, sorta. Okay, x and y are not multiplied together. X and y should not be denominators. That's okay. They should not be radical signs. That's okay, there's no square roots in there. But x and y should not be exponents. We have an x and there's an exponent there, so that one is non-linear. Okay, and now our last example for our notes. Which of the following equations is not a function? Okay, so well, first, we've said already that this one, that's a linear function, right? Okay, so that's a linear function, so it is a function, which means we don't want that one. We want the one that's not a function. This one, well, let me come back to that one. Okay, because I don't know. That one's a linear equation. I don't know if it's a linear function, though. Same thing right here. I know that's a linear equation. This leaves us kind of in a pickle here. Okay, so this one right here, I'm just going to go ahead and tell you what the graph looks like. If you actually type this in your calculator, it'll show you. So there's what the graph looks like. Is that a function? I took a vertical line test. I would only cross once. That one is a function. So that's not it. This one, if I multiply by 3 over 2, that's y equals 3 over 2x, which actually looks like this. Passes the vertical line test, that's a function. So we don't want that one. And this one actually looks like this. is this one going to pass the vertical line test? Where could I put my vertical line and be right on top and hit this thing twice? Well, right there at -1. Right there at -1, it would hit a bunch of times right there. So that one is not a function. And there we are.